Okay, yeah, so the TBA, because so the organizers for this workshop, I think the title of the workshop has something about future directions in it, and so the organizers of the workshop asked me to do some sort of more general kind of talk about future directions. So I don't know, I mean, I don't pretend to have any sort of crystal ball or anything. So I'm not sure I can predict any kind of future directions, but so this will be some sort of a potpourri of, open problems, and maybe, there will be sort of the easier, I start with the easier kind of open problems in the sense that that's the kind of problems where I think that now we have pretty much all the tools that you need to solve them, and in a way they should be some of them relatively easily within reach, and it just needs some work, and some of them maybe not so easily, but still there should be the tools around. And then maybe I mention a few kind of harder open problems where really I have no clue on how you would go about solving them, but there would be interesting problems that, hopefully maybe if we meet again in 15 years' time, somebody will have made some progress on that, maybe even earlier. So, okay, so let me start. So one type of questions which I thought is kind of interesting. So, okay, so this is going to be from my perspective as well, right? So it's sort of personal perspective, and so obviously it's not going to be balanced somehow. And so I don't make a huge, so one type of questions that I think is quite interesting and has sort of come up recently is the role of symmetries and in particular somehow the role of symmetries in order to sort of better understand randomization of these either singular SPDEs or any kind of singular probabilistic objects. And so for this I wanted to show you actually a very neat little argument which shows one way in which you can use symmetries in order to actually say quite a lot about randomization constants. And since the argument is very, very short, so I thought I'd actually just show you the argument almost from A to Z. Hopefully it's not going to kind of use up all the allotted time, but it shouldn't take more. I thought it shouldn't take more than 5 minutes, but let's see. Of course it's going to take more. So here the question's the following. So does this, so if you take the following class of SPDEs, so if you have this essentially a stochastic heat equation with some sort of KPZ type nonlinearity, so dxu gamma, and then here you have some sigma I alpha of u psi I. So you take that class of SPDEs, but you really view it as a class, so in the sense that you look at sort of all these SPDEs with all possible choices of gammas and all possible choices of sigmas and all possible dimensions for these indices, okay? And then you try to build solution theories for that, and of course there's all sorts of problems because of products being ill-posed and so on, but by now we have pretty much a black box that sort of built solution theories for you. And what does the black box tell you? So the black box, here it tells you, in this particular case, it tells you, well, there exists, basically there's a 54-dimensional space of randomization constants, right? So there's a space S, which is basically isomorphic to R to the 54, except that you should think of it as a sort of symmetric space. So it's R to the 54, but where you don't actually know where the origin sits, right? So it's like a space isometric to R to the 54, but it doesn't actually have an origin, right? So you have this space, and then you have an evaluation map, epsilon, which depends on gamma and sigma, which goes from that space into sort of smooth functions or smooth vector fields if you want, but not really vector fields, but functions with one free index. And with the following property, so that if you look at the slightly larger class, where here you also add like a vector field, so you add an H alpha here of U, okay, and I write U epsilon of gamma, sigma, and H, I write this as the map that takes as an input, you know, the gamma, the sigma, and the H, and spits out a solution theory. So solution theory would be a map from initial conditions into stochastic processes, right? So for fixed gamma, sigma, H, this guy is a map from initial condition to stochastic processes, which just gives you the solution, or the law of the solution to this guy, okay? And now there's a natural action here of the group of diffeomorphism of this thing. So one thing you can do is you can look at the law of that guy, and then apply a diffeomorphism to it, and so you get a new guy, okay? So you have if a phi is a diffeomorphism, then you have an action of the diffeomorphism group, which here the action is just given by take your stochastic process and apply your change of variables to it, right? And then here, you know, if say you mollify that noise, so you just view that guy as a smooth guy, well, there's also a natural action of the diffeomorphism on the class of equations, which is you apply the chain rule somehow, right? So you try to write an equation for phi of u, and then if you do the calculation, you find out that the equation for phi of u is again of the same type, but with a different gamma and a different sigma and a different h, right? So there's an action of the phi on the gammas, on the sigmas, and on the h's, so that this identity holds, right? But this really just says chain rule holds, okay? So that's my symmetry here. And now you want to say, what does this tell you about, you know, renormalization about that space or something? Well, so the black box theorem says that you can renormalize that equation to make it converge to a limit. So as epsilon goes to 0, this thing doesn't have any reason to converge, but the black box theorem tells you that there exists C epsilon in that space S, okay, such that the limit as epsilon goes to 0 of the U epsilon of gamma sigma H plus this epsilon gamma sigma applied to C epsilon exists, right? So let's give it a name. So whatever. So this is U of gamma sigma H. Okay? So the theorem, so that's by now a black box theorem that just tells you it's possible to find these constants. There's more or less an explicit formula for them, so that this limit exists. Okay? And so now you have you have an actual solution theory, which doesn't involve an epsilon anymore. And then you ask yourself, you know, can you guarantee that that solution theory somehow behaves in the correct way under changes of variables, right? So you would want this identity to be true also for the guy without the epsilon, right? So that's the thing that usually, in some sense in the physics literature, you sort of do it without thinking, because they don't really talk about renormalization of these things, so you kind of write down the equation formally, and they say, well, you do a change of variables, and you just formally write down the new equation. But for this to have a meaning, you would want to say that, you know, there's a way of taking these limits so that the limiting guy behaves in the correct way under your symmetry, right? Now, in general, there's no reason why this would be true, because, you know, what does this tell you? So you would want, right? So you would want the C epsilon to belong to some subspace, say S geometric, subspace of S, which would have the property that, right, so if you want this identity to be still true at the limit, it means that in here you would want to be able to replace H by H plus this guy, right? Now the H is something which is supposed to transform like a vector field on the changes of coordinates. So you want that guy to transform like a vector field on the changes of coordinates, right? And so you would want to say that if a guy is in this geometric subspace, if and only if, that's the definition of this geometric subspace, if and only if, when you act with phi on epsilon gamma sigma, then that's the same as taking the epsilon on the the gamma and the sigma on which I've acted on with the space with that diffeomorphism, right? So this here, so yeah, thanks. Right, so this here tells you this guy transforms like a vector field. Okay, so this is the identity that sort of says this guy transforms like a vector field. So if you want any chance of your change of variables formula to still be true in the limit, you better take here guys that transform like a vector field, right? But that's in general a subspace which is really not the whole space, right? And now this black box theorem doesn't tell you anything about, or it tells you something in the sense it gives you a formula for these things, but the formula is so horrible that it's typically not easy to check whether it actually lies. So typically it doesn't lie in that subspace, but then you would like to say, well, if it doesn't lie in that subspace, it doesn't matter too much as long as you lie sort of distance order 1 away from it, because then you just replace this by some guy which is in the subspace, and as long as it's distance order 1, then you would still converge to a limit, right? If the distance converges to a limit. Okay? And so what I want to argue now is that this is actually basically always true. Okay? So you can always, so if you have an approximation which has a certain symmetry, then you can always choose this guy in such a way that the limit has the same symmetry. And the argument is very simple. Well, so it seems to be a kind of general principle, so we have proofs in various special cases. So in this special case, the proof goes as follows. So it relies on the fact that this constant here doesn't depend at all on what the gammas and the sigmas and the h's are. It doesn't depend on what the dimension of the space is. It depends on nothing, right? So there's an explicit formula on it which involves heat kernels and stuff, but it doesn't depend on the data that you stick in here, right? So it's the same constant here. So it's this valuation here that gives you the data dependence, right? So these constants are just 1 over epsilons and stuff like that, right? So in particular, and you also know how this guy is, so this guy is typically sort of polynomial in these gammas and sigmas and their derivatives. So in particular, you can actually write your space S, you can decompose it as a direct sum of SKs, let me write like that, such that if you're in SK, this guy has the property that if I multiply sigma by some number alpha, right, then that's the same as just having alpha to the k coming out. Right, so like so tau in SK. So that's the definition of SK. So these guys are sort of monomials in the sigmas and the gammas, so they have a degree. So this just says you're in SK means that you have degree k. Okay? And then you can show that this subspace here typically sort of splits over that decomposition. So this geometric space is sort of diagonal with respect to that decomposition. So it has itself the same sort of decomposition. Okay. And now once you know that, right, you're basically done. Because, so what do you want to do? So you want to say, well, I have my constant C epsilon. So of course I can always split it into sort of a geometric part and then plus sort of the perpendicular bit, right? So you have a subspace, there's some complement to it. You can put a scalar product on these things if you want, right? So you can split this as something in the in that subspace and some complement. And what you would like to prove is that this guy actually converges to a limit, right? As epsilon goes to 0. And so what you do is you say, well, assume it doesn't. Okay, you go by contradiction. So you say, well, assume that the C epsilon perp goes to infinity. I mean, in the sense that some norm of that guy goes to infinity, right? So there's still an element in some vector space. So then what I do is I write alpha epsilon to be 1 over the norm of this C epsilon perp, but where here I take a sort of homogeneous norm. Okay, so I say the homogeneous norm of this guy is actually the sum of the norm of the kth component here, but to the power 1 over k. Something. Okay, so that they all sort of scale in the same way. Yeah. So you take this sort of homogeneous norm of this guy, and then I define alpha epsilon to be 1 over the homogeneous norm. So if this guy goes to infinity, this goes to 0. Okay. So now you look at the u epsilons of gamma and alpha epsilon sigma. Right. And, well, here I just put my epsilon gamma sigma, well, alpha epsilon sigma, applied to C epsilon. Right. So we know by the black box theorem that this goes to a limit. And the thing is that this conversion is very stable. So it's stable, it's continuous sort of in the sigmas and the gammas. So even if these depend on epsilon as well, that's fine. So this limit here is continuous in all that piece of data, right? So that tells you that this guy converges to u of gamma 0, 0. Okay, so now u of gamma 0, 0 is just the solution to the deterministic equation, right? Now, on the other hand, so here, well, on the other hand, what I can do is I can split this guy, right? So I have this splitting into the geometric part and the perpendicular part. And now by construction, the bit, this bit here, actually stays bounded, right? So by construction, because of the way I define the alpha epsilon, if I look at the epsilon gamma alpha epsilon sigma C epsilon perp, right? So that's a sum over k of, so you have this homogeneity in the kth component, but alpha epsilon to the k is actually just, basically 1 over the norm of that guy. And so this, right, so this converges, this remains bounded, right? So remains bounded. And this is actually the same, right? Because this is the same as taking the sum over k of the epsilon gamma sigma and applying it to alpha epsilon to the k times the component here in the kth subspace. Right? And what we've chosen the alpha epsilon precisely in such a way that each of these guys remains bounded. Right? And so then just by compactness of unit balls and stuff like that, you can actually take a subsequence so that these guys converge to a limit. okay? And at least one of the limits, at least for one of the k's, the limit has to be non-zero, because the total norm, I've sort of normalized it so that the actual norm is 1. Right? So it stays away from the origin. So you get a non-zero limit for this, guys. So let me write V to be the sum over k of this alpha epsilon to the k c epsilon perp kth component. Okay? So that's the limit, if you want, the limit as epsilon goes to 0 of this thing along a subsequence. Okay? But just by some compactness, I have a limit along some subsequence. And then what you do is you say, well, here I actually keep only the geometric bit, because the other bit, what happens to the other bit? Well, the other bit gives you a correction like that, which converges to a limit. And so it means that it's exactly the same as if I had put here minus the sort of epsilon gamma sigma of that limit, V. Right? But now, here, I have an approximation which behaves in the usual way under change of coordinates. Right? So it means that guy behaves in the usual way under change of coordinates, which means that that guy has to behave in the usual way under change of coordinates. But that guy is just a deterministic PDE. It's just that PDE plus whatever correction term that gives you. Now that PDE, the first bit, behaves in the usual way under change of coordinates. And so if the solution behaves in the usual way, that means that, you know, that extra bit that you've added has to transform like a vector field. Right? But by assumption, this guy lives in the perpendicular space. And so the definition of that perpendicular space is that it doesn't transform like a vector field. And so you get a contradiction. Right? And so it means that this guy actually had to be bounded. And then once you know that this guy has to be bounded, you can do a similar sort of argument. You can sort of redo a similar kind of argument to also say, well, it's bounded. I want to show that it actually converges to a limit. But then you do the same thing. By compactness, there are subsequences that converge to limits. And now by contradiction, assume that you have two subsequences that converge to two different limits. And again, you do the same splitting. And then you find out that you get a contradiction, or at least that you find that the component in that perpendicular space isn't allowed to converge to two different limits along two different subsequences, because you get exactly the same sort of contradiction. Right? So that's a pretty general kind of argument, right? So it tells you for free, for example, in this particular case, this space is 54-dimensional. This subspace here is 15-dimensional, okay? So it tells you for free that out of these 54 randomization constants, 39 converge to finite limits, right? Without having done any calculation, okay? Whereas a priori, these things are given by huge, horrible multiple integrals, where it's very difficult to figure out whether they converge to a finite limit or not, or which linear combinations of these guys converges to a finite limit or not, right? Whereas here you've done sort of a 5-line calculation, and I have not hidden anything, right? So there's no cheating going on here. So it's an honest 5-line calculation that tells you that out of these 54 randomization constants, 39 converge to finite limits without doing any line of hard calculation, right?
Where did the 15-dimensional calculation come from?
Yeah, that's a harder calculation. Yeah, okay, so it's not right. So of course you have to be able to figure out what that space is, and that's harder, right? But you can do a similar thing where instead of doing change of variables, you say, well, there's another formal thing which says that this is supposed to have some sort of E to isometry, which is that if I take two different sigmas, so that sigma sigma transpose of the first guy is equal to sigma sigma transpose of the second one, you should get the same law, okay? Do exactly the same argument, it still works. You can do exactly the same analogous argument. And that tells you, well, there's another subspace here, which is the Ito subspace somehow, which satisfies this kind of Ito isometry, which is a 19-dimensional subspace in this case. And then where again, so you know a priori that actually the components that are outside of that other 19-dimensional subspace actually have to be finite. And then you can ask yourself, well, so maybe it could satisfy both. And so there it's not obvious, because the problem is that you can't find any approximate, right? So it relies on the fact that at fixed epsilon I have some way of approximating the thing which satisfies the symmetry. And you can find some way of approximating which satisfies the chain rule. You can find some other way of approximating that satisfies sort of E2 isometry. I don't know of any way of approximating it that satisfies both. Okay, and so in general, so for example for SPDEs, well, you know that you can't have both. You can have either the chain rule, then it's Stratonovich solutions, or you can have E2 isometry, there's E2 solution, and you can't have both at the same time. Right? So here it turns out that you can, because there's a sort of similar type of argument that still actually works. And that turns out that you can. And so if you combine both, that actually tells you a priori that in this 54-dimensional space, there's actually only two directions in which the randomization constants can potentially diverge. Right? So you get a lot of mileage actually out of these symmetries. Right? So you have a priori, you have some horrible explicit formula for these things, right? That looks like it's diverging like hell. But it tells you that actually in this 54-dimensional space, you can find 52 linearly independent linear combinations of these constants that are guaranteed to converge to finite limits. And there's only two remaining linear combinations that can potentially diverge. And so that's something, so that's sort of the first, if you want. So this is obviously not an open question, that's just a 5-line calculation, right, which works. The question is more to sort of understand better how this interplay in situations where you have more than one symmetry and you can't necessarily figure out one way of approximating that satisfies all of these symmetries simultaneously. The other thing is that also, for example, the argument in the Ito case is somewhat, it's very, very similar, but it's not quite the same, and so it's not completely clear either what the correct meta theorem is, if you want, that sort of includes all of these. So there's a similar thing happening in Young-Mills also with gauge invariance. You can do a similar kind of argument. But again, in the details, it's actually different. And so it's not completely clear how to formulate. If there's a nice way, it would be really nice to have one way of formulating these things so that these are sort of special cases of one statement. But it would be particularly nice to sort of understand how things happen in, how things behave in situations where you have more than one symmetry and you can't a priori find one approximation that satisfies all of them. Anyway, okay, so, right. So that was first out of 15. So now there's another, okay, so there are other, still sort of open questions that are, if you want, semi-open in the sense that, you know, like here, one has in principle, one has pretty much all the tools to answer these kind of questions, right? Another sort of similar type of questions where in principle the tools are there, but there are bits missing, is, for example, to understand a bit better what happens when you have non-trivial boundary conditions. And what happens when you have boundary conditions for these singular SPDEs is that sometimes you can have randomization happening at the boundary as well, not just in the bulk, if you want. So you can have boundary randomization. And this happens in situations, well, so like, for example, in 543, this happens in principle if you take Neumann boundary data. So, for example, for 543, what seems to happen is that if you take 543 equation in a domain with Neumann boundary data, so just derivative equal to 0 on the boundary for some approximation, and then you try to pass to the limit and you do the usual way of renormalizing it, it's not clear that you actually get a limit. So it might be that you have to adjust the boundary condition so that the divergence the normal derivative is not 0, but it's actually something that diverges. And it has to diverge in exactly the right way, just as you have the bulk randomization where you have to add a linear term with a constant in front that diverges just in the right way. And so this actually happens in situations where you have, so like in 543, the reason why it happens is that this guy has scaling exponent, if you want, -3/2 in 3 dimensions, right? And -3/2 is less or equal to -1. And the reason why -1 is important in this business is that if you have a domain, the boundary of the domain always has codimension 1. Okay? And that's D1. That's the same one. Okay? And so generally what happens is that if you're in a domain and you look at an equation where in some sense, the dominant nonlinear part, so here there's a worse part, so that guy scales like -5/2, which is even less than -1. But that's not nonlinear, right? So that's just the noise itself. And so noise, you see the problem, what happens is that if you take a distribution here of order, an element of C alpha, so if you have a distribution of order alpha, if alpha is less than -1, there's no canonical way of extending it to a distribution in the whole space. Okay? So in the sense that distribution inside the domain means you test against test functions that are compactly supported in the interior. Okay? Now, of course, you can always say, well, if you're outside, then you're 0. But what happens if you test against a test function that sort of sits across the border like that? Because you can sort of chop it up into little pieces. You can write it as a sum of test functions that kind of sit both either inside or outside. But then when you do the power counting, you see that if alpha is less than -1, that sum might fail to converge. Okay, and if alpha is bigger than -1, it's always guaranteed to converge. And so that's exactly the kind of problem that happens here. And so we sort of understand what happens, but for example, it's not clear at all. So there's no theorem whatsoever in situations where, well, you have domains like that, right? So it's not clear, for example, how in this boundary randomization curvature of the boundary plays a role or things like that, right? So there are quite a lot of open questions in that direction. So even we don't have anything like a general, so for example, with AJ, we have this quite general black box analytical result, which in particular gives you these kind of convergences. But that's really a sort of bulk. It makes use of translation invariance. And so here, because you can always embed this in the whole space, so you sort of build these objects still in a translation invariant way, but then you have to somehow deal with the boundary. And that's, at the moment, we have a couple of results, but they are sort of ad hoc, more or less, right? And so they rely, again, on doing some of the analytical calculations by hand on a case-by-case basis. It would be nice to understand that sort of more generally. And sort of in the same direction, there's, I mean, this whole black box kind of theory works extremely well in situations where your approximation is itself already a continuum sort of problem, right? So here, I take an approximation where I smoothen out that noise. The approximation still lives in sort of continuous space-time, okay? Now, of course, what you would really like to do is link these kind of things to statistical mechanics models, right? And so in statistical mechanics model, you start from a model which is on a lattice. So, yeah?
Sorry, this extension you said fails for alpha less than 1. That's in the deterministic case? Or is there a chance for some...
Right, so it's in the deterministic case. So if this guy is just a Gaussian process, right, then typically you can go below. Then it actually fails at -2 somehow, right? Because you always double things up in the Gaussian case, right? Because it's really the correlation function that you need to be able to restrict, and that one sort of behaves like the, right? Sort of it doubles up to the exponents. But if it's not Gaussian, right, then in general it really fails. I mean, so we have in the case of KPZ, you're just in the borderline case in the sense that the dxu square scales exactly like -1, and we can prove that you have an order 1 effect from that thing, right? So that shows that if you're actually just in the borderline, you do actually have order 1 effect, even in the stochastic case. But it's only because it comes from a nonlinear term, right? So it's the term, the nonlinearity, which has scales like -1, and that gives this order 1 effect, and which you see in several instances. So there's a paper, I think, by Howe and Ivan also, where they see a similar kind of effect on a discrete, from a discrete approximation to KPZ. Right, so in the discretization, what you would like, also, by the way, so how's the time going here? Do I have until 11 or until quarter 2?
Well, a little bit before 11.
Okay, good. So, right, so for example, there's this result by Hendrik Weber and Jean-Christophe Morin, where they can show that if you take an Ising model with somehow relatively long-range interactions, if you take a simultaneous limit where you sort of put that Ising model at the critical temperature or close to the critical temperature, you send the range of the interaction to infinity, but you rescale the system, so you look at it at a scale which is larger, much larger actually, than the range of the interaction. If you go to the right scale, then it converges to this singular SPD in dimension 2. And probably the tools are more or less there to do it in dimension 3, but that's also still an open problem. But in that case, of course, you know, you have sort of a discrete approximation if you want. In this particular case, it's kind of nice because for this particular Ising-Katz sort of model, if you look at the right observables, you can find a set of observables for which, when you apply the generator to them, you get something which is again a function of exactly those observables. So that gives you an approximation that already looks very much like a sort of numerical approximation to that SPD, with the exception that somehow the noise bit is replaced by a bunch of martingales, of which you somehow know the quadratic variation, but it's not, you know, they are not Gaussian processes or something, so they are not just IID noises on the grid points or something like that, right? So they have non-trivial quadratic variation, and they actually jump processes and so. And so right now, when you're in situations like this, you know, you still pretty much have to actually do everything by hand, right? And so that's why they have a result in 2 dimensions where there's not too much stuff you need to control, and in 3 dimensions it seems that it would just be extremely painful to get a similar kind of result, right? And so that's where, again, you get some mileage out of having a more systematic way of approaching these type of problems where you have sort of non-Gaussian, sort of discrete kind of approximations, and get sort of analogs of like the analytical results we got with AJ, for example, or stuff like that in this discrete setting. Now, so a nice open problem would be also, if you take this 5-4 equation, so in 3 dimensions, for example, so now we have extremely good global bounds. So there's, for example, that very recent paper by Hendrik Weber and Moina, and there's also a paper by Max and co-authors and Martina. So there are a number of papers that came out in the last couple of years that give very good a priori bounds on solution to this equation, also in 3 dimensions. And so, for example, one thing is, well, obviously, it's expected to have a phase transition if you look at this in the whole space, right? So what you expect is that you can tune this value C, and there's a critical value C star, and for larger values than that, you have 2 invariant measures, the whole space, and for smaller values, you have only 1 invariant measure, okay? And it would be nice now to actually be able to recover results like that, basically by using PDE techniques, exploiting the fact that since you have extremely good control over this, so you have local control on the solution, even though the equation is on the whole space. So you have a priori, so it's like Harnack inequality type thing, but for this equation, in the sense that you get control at a point in space-time, if all you know is some kind of control on the noise, in some parabolic kind of ball behind that point, and you don't need to know anything else. Since the control that you get is uniform over all initial conditions, everything that you want that happens outside of that little neighborhood. That comes from the fact that this minus q cube is sort of extremely strong. So it dampens things down extremely strongly, right? So you get this extremely uniform control. And so then what you would expect is that you could sort of break up R3 into sort of patches of roughly order 1. You have very good control over what happens in each patch. And then if that constant is sufficiently negative, then that control would be sufficiently strong to somehow say that, well, you have some kind of approximate ergodicity in sort of order 1 time in each of these patches, right? And then you need some kind of argument a la Dobrushin that kind of, you know, puts these patches together and gives you a similar kind of result in the whole space, right? So this is relatively well known how this works for, like, you know, probabilistic cellular automata somehow, right? And so this would be almost like a probabilistic cellular automaton where each site is a patch, sort of an order 1 patch of R3. So then, well, so since I'm sort of on the global solution somehow, well, for this particular problem, we now have extremely good control. And so you have global solutions in time, but also global in space. Things are much, much less well understood in, you know, situations like that one also. So where you have, where in principle, so for example here, if you forget about the noise, you can find some sort of energy function that decreases. This is basically a gradient flow. And so again, you would expect to have global solutions just because of that. But the sort of techniques that apply here really don't seem to apply here, right? So it would be very nice to have a somewhat more general machinery to get global solutions, something that somehow allows you to, you know, something analogous to what you would do in the deterministic case, right? In the deterministic case, you know exactly what you have to do. You have to somehow find some kind of Lyapunov function or some energy functional that somehow decreases, right? So you want to find some kind of functional on your solution space that sort of decreases along solutions. And so you'd want to do something similar here. So you want to find some Lyapunov function also. But of course, the usual thing about, you know, guessing your Lyapunov function and then sort of applying the generator to it to see if you get something negative fails sort of miserably because the generator for these things is very badly understood, and there's no, typically smooth functions aren't in the domain of the generator. Sort of smooth functionals of the solution are not in the domain of the generator, and so you can't do that, right? And so there would be, it would be nice to have still kind of a more general, yeah, some kind of technology that goes in that direction that allows you to build Lyapunov functions for these things. Yeah.
Is the gamma negative definite in this equation?
So in this equation, the gamma would be Christoffel symbols for a manifold, for example. So it doesn't have to be negative definite, but the thing is that, so if the gammas are the Christoffel symbol for a manifold, then the energy in the differential geometry sense is a Lyapunov function for the for that part of the equation. So this is just a gradient flow for the energy functional in the intrinsic sort of L2 structure that you have on the tangent space. Okay, so then, and then sort of the last type of open questions that I wanted to mention, which is still in the, you know, collection of open questions that should be within reasonably easy reach of what we've got now, is somehow hyperbolic or dispersive problems, right? So there's a, for example, there's a nice recent paper by Tadahiro and Max where they look at a wave equation dt square u Laplacian u. So you look at the simplest non-trivial case where this guy is space-time white noise and you're in dimension 3. And you ask yourself, you know, is there a way of renormalizing that nonlinearity here, right? and things get much trickier. So we have worked in progress with one of my postdocs as well, where we look at the same problem. And what seems to happen is that, well, so you can try to play similar games as what you would do in the parabolic case. Power counting is much less clean in the sense that you can conjecture a power counting, but then there are some objects that actually behave better, which typically doesn't happen in the parabolic case, but it happens in the hyperbolic case. And so then you want to exploit that. And the other thing is that in some sense the group of translations plays much more of a role, because singularities somehow move around in space, whereas in the parabolic case, you know, singularities don't move. They kind of stay where you are, and they sort of immediately get killed by the linear part of the equation, and they just get recreated by the noise somehow. Whereas here they really move around, and so you have to understand better somehow how the action of the translation group sort of interplays with all of your sort of probabilistic objects. And here what seems to happen is also you don't need to, right? So in these kind of parabolic sort of problems, ultimately you just need to control essentially a finite number of probabilistic objects, and then you can build a solution map which is some kind of deterministic functional of these probabilistic objects. Here it seems that you really need to build, so the probabilistic objects themselves are more like random operators also. Right? So you sort of go up one layer in the level of abstraction. And so again here, that's really sort of at the beginning, so there isn't a good understanding yet of what's the clean way of formulating these type of problems. Okay, so now on to the science fiction part of the talk. So what would be, so some really hard, nice problems. Well, so one, for example, if you take the nonlinear Schrödinger equation, which is sort of that one where you stick an I in front here, and there's no noise at all. So you take the deterministic nonlinear Schrödinger equation, right? Formally, the phi-4 measure is invariant for that. And in 2 dimension, that's somehow a famous paper by Bourgain from the mid-90s, where he showed that indeed you can sort of define, if you want, the solution to the nonlinear Schrödinger equation for which the 2-dimensional phi-4 measure is invariant. Okay, do that in 3 dimensions. That seems to be hard. The somewhat easier problem that's maybe halfway in between is if you take a damped wave equation like that. So if you take this equation and you stick in a minus u dot and you put a cube here, maybe with a minus, then this one is also formally has the phi-4 measure as invariant measure. Okay, so that should be sort of halfway in between in terms of difficulty. Okay, so that one. So don't try to understand that without first having understood that, because I don't believe that there's any way of understanding that. If you understand that, then you can probably understand that as well, and that one should be significantly easier.
That's okay in 2D?
That one is okay in 2D, yeah. Well, that one's also okay in 2D by the result I will go. And I think that one would be easier to prove in 2D than that one. Now, another thing is sort of trying to understand, right? So one of the goals of this whole singular SPDE business is to understand a bit better these renormalization group picture. And what these SPDEs tell you is, in some sense, they allow you to understand crossover regimes sort of between Gaussian fixed point of the renormalization group and sort of nonlinear or non-Gaussian fixed point of the renormalization group. For example, in the case of KPZ, that would be, so here you would have sort of the Edwards-Wilkinson model, which is just stochastic heat equation, and you'd have the KPZ fixed point, which I suppose Jeremy is going to talk about later this week. And the KPZ equation is somehow in the randomization group picture. It's sort of the heteroclinic orbit that connects these two, which is conjectured to be unique in a certain sense. And you can draw similar pictures for a number of these singular SPDEs. So that they allow you to describe sort of what happens in the neighborhood of a Gaussian fixed point of the randomization group. Is it possible to build similar kind of theory that allows you to describe what happens in the neighborhood of some non-Gaussian fixed point of the randomization group? Of course, the problem there is that there are not many non-Gaussian randomization group fixed points that you can even describe. But there are a couple of ones. Okay, so that one is a hard one. So that one you can describe, but the description is horrible. I suppose Jeremy is going to tell you about it, but I think it's fair to say that it's still horrible. No, it's not horrible anymore. Well, it's very complicated. Okay, it's complicated. But you have an explicit description, right? So this guy is fairly well understood. But there are simpler randomization fixed points that are sort of free in some sense, but are still not Gaussian, that are much easier to describe. And again, you would expect to have similar kind of, you have crossover regimes near them, near those. And it would be nice to have some kind of machinery to describe these. And along the same lines, it would be nice to have a machinery that goes the other way around, in the sense that, so this whole machinery looks at situations that are sort of super renormalizable at small scales. And if you go in sort of high dimension, typically you end up at some point to be in a regime where you're super renormalizable at large scales. And so it would be really great if there was some sort of more general way, right? So pretty much the only general methodology that, at least I know, maybe there are others, to deal with situations that are super renormalizable at large scales is the lace expansion. But it would be nice to have some kind of more general way of dealing with these for, random PDEs, if you want, that are super renormalizable at large scales in order to get scaling limits of these. So really nice open problem would be the one to show that in 2 dimensions, if, right, so here there's supposed to be a phase transition for this value of C. So you choose the C to be the critical one, and you take the 542 measure at the critical value, and then you rescale in space. Okay, you're supposed to get the same limit as the one that Christoph and Chuck Newman and company got for the easing model, right? So you take the critical easing model, you look at the magnetic field, you rescale it at criticality, you rescale it, there's a limiting random field, which is non-Gaussian, with scaling exponent, is it -1/8 or 1/4 or something, depending on how you count. I suppose 1/8 with that way of counting. And the conjecture is that this guy is supposed to be the same limit at large scales. And that's one of the super hard problems, I would say. And then, of course, there are the problems that are kind of super renormalizable at small scales. There are the ones that are super renormalizable at large scales. In the middle, there are the ones that actually just somehow are formally scale invariant, if you want. So the ones that are just renormalizable. And of course, the most famous one there would be Young-Mills in 4 dimensions. And so, of course, somehow, one of the major open problems would be the $1 million Young-Mills question, which you can, I think in this, okay, so it's not completely clear what counts as a solution to that problem, which gives you the $1 million, but probably one, I don't know if that would count, but certainly one conjecture that you could formulate is you take the Young-Mills, so you can take a stochastic version of Young-Mills, you can write it down in 4 dimension, So you want to build an actual stochastic process that corresponds to that, and you would furthermore want to show that you can do that in the whole space, and you have kind of spatial decay of correlations. Okay, so that would be something like the mass gap. And the reason why this has a chance of being true, I mean, you see here, that depends on the value of this constant. Right? So depending on the value of the constant, either you have one invariant measure or you have two, and correlations either don't decay at all or they decay exponentially, at least conjecturally. In Young-Mills, if you want, the gauge invariance somehow gives you a lot of rigidity. And so there's no degree of freedom left. Right? So there isn't really an analog of that constant that gives you the phase transition. So there's no degree of freedom. And so somehow either you're in one case or you're in the other. Right? There's nothing you can tune. And the conjecture seems to be that you're in the case where the correlations are supposed to decay, and if you can prove that, then you can probably cash in the $1 million. And then, so finally, I think one very nice open problem that would be, I think that's conjecture for Jeremy somehow, would be the one, take the Kuromoto-Shirazinski equation. So the Kuromoto-Shirazinski equation, you know what I'm going to mention. Okay, so it's, you take this equation here. So dt, say h. It looks like the KPZ equation, but the heat equation part has the wrong sign. Okay, but then you compensate by a quartic term. Okay, so you look at this equation here, deterministic, nothing random here. Okay. It's somehow a bit like KPZ without anything random. The difference is that the spectrum of the linear operator, instead of being, just a parabola like this, it actually looks like this. Right? So the spectrum somehow looks like this for the linear operator. And what it tells you is that it sort of excites modes at wavelength roughly order 1. And so it's all self-sustaining, right? And so the fact that it excites these modes at wavelengths of order 1, and numerically you have some kind of chaoticity, that suggests that it should actually be, if you want, you don't need the noise in order to converge to the KPZ fixed point, right? So what you would expect is that if you start with a more or less generic random initial condition, so you start with an initial data which essentially rescales to a Brownian motion, so you take random initial data which looks like a Brownian motion, also you stick it into this, and you rescale the solution at large scales, should converge to the KPZ fixed point. Right? Again, I think that's the open problem for Jeremy to solve. He's going to tell you how to solve it in his 2 lectures. And so I think I'll stop here. Thank you very much.
And for some questions?
I have a question on your black box. I mean, when you look at the KPZ equation, I mean, usually there are also terms of order, linear dx of u. I mean, not dx squared.
Oh yeah, that doesn't matter. You can add those. That makes no difference.
No,
yeah. That makes no difference. Yeah.
What about adding quench noise in your equation? Is it part of the future or not?
Yeah. Well, right. Okay, so that's so. Okay, so I think the question that you asked, it's sort of part of the. Okay, so in this black box, it doesn't care about this noise being, time dependent or not somehow. But I think for the problem that you have in mind, what's missing is a similar kind of, So if I mentioned that we don't have a good black box for discrete approximations yet. The other thing is we don't have a good black box that sort of deals with situations where you have somehow you get additional terms, so you have somehow expansions on the right-hand side with terms that have epsilons in them as well. And you know, what can happen is that these terms formally they disappear, but then because of randomization they actually have an order 1 contribution to the limit. And again, like in the paper with Jeremy, we have something like that, for example. And you know, you can, again, it's the sort of thing you can deal with it by hand. And so in this kind of quenched KPZ thing, so in the sense that, so I think the problem that Pierre is thinking about is the following, right? So it's you take a two-dimensional random environment. So you have your two-dimensional plane. You have a, say, smooth random field on the two-dimensional plane. You start with some initial condition, which is a line somehow in this two-dimensional plane. And now you evolve according to a directed mean curvature flow. But where the speed, the normal speed, depends on your environment, right? So the normal speed at this point is, say, 1 plus the environment at the point. And then what you expect is that if the environment is relatively weak, and you start with something which is sufficiently straight, then at the correct scale, this is supposed to converge to the KPZ equation, the usual KPZ equation, because you just run through the environment, right? And then, although here the environment is sort of static, but you essentially run through it at somehow speed of order 1, and so it's as if you had space-time noise, and so you should converge to the usual kind of KPZ equation if the environment is sufficiently weak. And then if the environment gets stronger, then at some point there should be a transition to something people will call the quenched KPZ fixed point, I suppose, which would be a point at which this thing sort of starts to get stuck, and you have a sort of interesting long-range behavior. And so I think with these black box techniques, you can probably say something about the first regime, so the one in which the noise is weak, and you essentially converge to the KPZ equation because you sort of run through the environment. I don't think it can say anything, at least at this stage, about the regime where you start to get stuck. Yeah.
So with your 543 boundary value problem with conditions, if the boundary is, if it's a half space, presume that's very easy in that case, or not?
Yeah, first it's easier when it's flat, right?
Right.
So for example, when it's a cube is fine, so I like the half space, yeah.
So can you, I mean, what kind of technology is there for straightening out the boundary by a coordinate transformation, which will give you a rather strange Laplacian instead of the one that you've got?
Right.
Is that something that...
Yeah, so I suppose that would be another one of the open problems, is to kind of deal with situations where you do change of coordinates of your domain somehow, right? And so at the moment, for example, this black box kind of theorem really relies on translation invariance. And so that straightening out wouldn't really help. It'd probably be easier to just look at the original coordinates. But
so you mentioned the stochastic quantization and trying to get a hold of the critical, I mean the phase transition point. So did you look at the fractional case? Is that any easier from SPDE method? Because from the RG, I think it's easier.
Right. So you mean you put yourself in the fractional case in such a way that you're sort of morally in dimension almost 4 somehow.
Yeah, 3 dimensions with the Laplacian to the 3/4 plus epsilon.
Right, which would be some sort of effective dimension almost 4 or so. Yeah, I don't know. No, I haven't looked at that.
I mean, you have non-trivial fixed points. It's a long-range model, Heisenberg. Ferromagnetics. You have non-trivial fixed points below the critical dimension.
Right.
The critical dimension is calculated in terms of the dimension and in terms of the decay.
Right. Right.
So you can get non-trivial fixed points.
Sure.
And so for non-trivial fixed points, you will find that your bare coupling that you have will go to infinity if you work against continuum. That's an interesting problem.
All right, so I think we should thank Martin again and go on.